Hello everybody, welcome back to the channel. Today we're going to talk about the single-phase circuit analysis. We're going to have three video clips, the three topics. And the first topic I'm going to introduce was the single-phase circuit versus the multiple-phase circuit, especially three-phase circuit. And then we're going to talk about additional way of calculating the complex power, because for single-phase circuit analysis, we are going to calculate the complex power for various components in the circuit. And then the second one is we're going to introduce the concept of complex power conservation. And that means all the complex power delivered to the components will be adding up to zero. And so there is a formal theorem which called the Tellegen theorem. I don't think I introduced it ever, so I'm going to include that Tellegen theorem here, and that's very general results. And then we're going to look at a single-phase circuit analysis example in the third video clip. Let's start with the first one. What is a single-phase circuit? Single-phase, if you have only a single source, the single AC source, that's definitely a single-phase circuit. But if you have multiple sources, you could still have a single-phase circuit. And for multiple surface, the single-phase circuit, will always single-phase circuit has the sources. If it has multiple sources, the sources with the same the frequency and phase angle If I draw the circuit in the phasor form, and that implicitly we're assuming that we're in the same phase. Otherwise, it doesn't make any sense if you put the phasors in different frequency in the same circuit, right? If you want to do that, you could use the superposition. Then you need to draw multiple circuit for that. Okay, and let's see for this first one here. And this has two sources, but they have the same phase angle, and implicitly they have the same frequency as well. So this is a single phase circuit. And for the second one here, the first source here has 120, has 0 degree, and second source has 120 degrees. So they have different phase angles, and therefore this is not a single phase circuit for the second one. Okay. And in fact, the first circuit is sort of mimic the circuit in typical U.S. household, and we have 240 coming in, and they're split to 120s. And in typical homes, we don't really have three-phase circuit; we only have single-phase circuit. Okay, and since we are going to calculate the complex power quite often, and we're going to introduce a couple of other ways of calculating the complex power. So the one we already learned is that if we know the current and voltage across through the impedance, and also voltage across the impedance, we know the S is going to be equal V times I conjugate. Here, V and I are in RMS value, not in the peak value, right? So, so in this case, if you know the voltage and the current both, right? But if you only know the voltage, you could find the current first, or you can do a step further, so you can get the complex power directly. If V and Z are given. And then we can replace the I by, so we replace the I by V over Z, right? So we have V times I now is V over Z, the conjugate, and therefore if you conjugate the ratio of two complex numbers, and then you can take the conjugate first and then take the ratio, and then we have v times v conjugate over z, and we know the v is v times v conjugate. That's going to be equal to v amplitude square over z, and so that's for the if you know the v and z. And if you know I and z, and then we can find s by s is going to be equal. Now we replace the v by I times z, and times I conjugate, and we know I times I conjugate is that's going to be equal to I magnitude square times z. So if the z is in the form of rectangular form r plus jx, right? And that one here is going to be, so therefore the s is going to be equal I square times r plus j I square times x. So this actually is the q, right? So this is the p. This is real power and this is reactive power. And if the reactive power is positive, so if the x is positive or z is inductive, and then q is positive as well. So that means we were delivering reactive power to the load, to the impedance, right? So that's the couple of additional ways. Although this is not really, completely different from the basic way of calculating the complex power. But if you know these additional methods, it will get things done quickly, more quickly. Okay. So next we're going to introduce the conservation complex powers by introducing the Tellegen's theorem. I'm going to see you in a next video clip.